Good morning to all. Good morning, children.
Good morning, sir.
Okay. So we will start our today's maths class. And today is the last day allotted for our maths class. Okay. So today I'm going to discuss something from the chapter relations and functions. Okay, from the beginning. Relations and functions. From this chapter also, you will be getting around 6 marks, not less than 6 marks. Okay. So let us start our relations and functions. Okay. So in this chapter, actually, there are two topics. One is relation, another is function. And both of these concepts you have studied in your class 11th also, the basic concepts. Okay, everybody knows what is a relation. Suppose we have a set A. Set A contains father and mother. Okay. And set B, son and daughter. Okay. Then we know what is meant by a relation from the set A to the set B. Everybody knows that a relation is a subset of A cross B. Okay. So we can take a different type of relations. Okay. Suppose I take a relation from A to B or from A to B. Defined by R equal to set of all ordered pairs A comma B, such that we can make some relation. Okay. For example, age of A is more than age of B. A belongs to capital A and B belongs to capital B. Means small a represent the element from the first set and small b is an element from the second set. For example, I'm taking this example. Okay, this relation. Now, what are the elements in this relation? We can list all the elements of this relation. Okay, definitely. The first set is father, mother. Second set is the elements son and daughter. So definitely the age of father will be more than the age of the son. So F will be there and F D will be there. Then M S will be there. M D will be there. So these are the elements of my relation. Okay, the relation defined by all ordered pairs A B such that age of A is more than age of B. This is one example. Okay. So every element is a subset of A cross B. So that's the meaning of a relation. Okay. Any relation is a subset of A cross B. In particular, the A cross B itself is also a relation. That is called a universal relation. And the empty set also a subset of every set. We know that. So that is also a relation that is known as the empty relation. Trivial cases only. And there was a question in our term 1 examination. Huh? For example, means almost same type. How many relations can be possible like that? How many relations are possible from the set A to set B? In that example, okay, in this example, how many relations are possible? Every relation is a subset of A cross B. So here A cross B has how many elements? 4 elements, isn't it? That means the number of relations equal to 2 raised to 4. Okay, number of relations will be number of subsets of A cross B. That's equal to 2 raised to 4. Okay. So in general, if a set contains m elements and another second set contains n elements, the number of relations from A to B will be equal to 2 raised to mn. Number of subsets of A cross B means 2 raised to mn. Okay. And we know what is domain. What is domain? Domain means all the set of all the first sets and sorry, first elements, and the range means the set of all the second elements. Okay, all these things are very fundamental things only. Just I am recalling. That's all. Okay. Now, what is we have to study on in 12th class? The relations are classified into 3 types. You know, 3 types of relations are there, having some special property. So the first one is a reflexive relation. Definitely, there will be a 5 marks question from this area, either to prove a relation is an equivalence relation, otherwise some function may be given, prove that it is 1, 1 and on to, etc. Okay. So, what is meant by a relation which is reflexive? When we say that a relation is reflexive, the definition, everybody knows the relation. A relation is said to be reflexive if R is the relation, then R is said to be reflexive if every element of A is related to itself. Okay, A comma A, we write mathematically, A comma A belongs to the relation. Okay, belongs to the relation for all A in that set. Okay, a relation in a set means the relation is from A to A. We are taking only the relations from one set to the same set. Okay, so if R is a relation in a set, means from a set to A to another same set to A, then we say that the relation is reflexive if A belongs to R for all elements A belongs to the given set. Means every element is related to itself. Every element is related to itself. So that is meant by the reflexive relation. Okay, every element is related to itself. For example, if I take my first set A is the set of containing father and mother. Okay, and I define a relation R equal to set of all ordered pairs A comma B such that A and B are of same gender. Okay, R is a relation in the set A given by ordered pairs AB are ordered pairs AB such that A and B are of same gender, means same sex. Okay, A and B both belongs to the same set A only. So what about this relation? So what are the elements if I list out? Then very clearly we know father and father is one element, okay? The same person means male and male, father and father, one element. Then mother, comma mother, M, comma M. Mother is related to mother. That's the meaning, okay? Father is related to father, okay? Is there any other element? No, we cannot take father and mother. Then this is a reflexive relation. Okay, every element is related to itself. Every element is related to itself. That's the meaning of the reflexive relation actually. Okay, now come to the symmetric relation. All these definitions you must be already studied actually. You must have studied actually. Just I'm recalling. Okay, just recall. So symmetric relation. When we say that a relation is symmetric, the definition is like this. Okay, a relation R in a set A is symmetric if the definition is like this. Okay, AB belongs to the relation implies BA also belongs to the relation. AB belongs to the relation implies BA also belongs to the relation. Okay, so very carefully we have to study the definition. If AB is in the relation, then BA must be there in the relation. That's the meaning. If AB is there, definitely BA also must be there. That means if A is related to B, if A is related to B, then B also must be related to A. Okay. So this definition we have to understand very carefully. We have to use it for doing the problems. Okay. If AB is there, then BA must be there. For example, I will take a example from our maths only. A is equal to 1, 2, 3. A is equal to 1, 2, 3. Just I will take a relation R1, 1, 2, 2, 3. Only this much. 1, 2, comma 2, 3. No, it is not reflexive very clearly. It is not reflexive because 1, 1 is not there, 2, 2 is not there, 3, 3 is not there. Okay. If 1, 1 is not there, it is not reflexive. Okay. For reflexive, 1, 1 must be there, 2, 2 must be there, 3, 3 must be there. For reflexive. Now, what about symmetric? 1, 2 is there. You can see very clearly, but 2, 1 is not there. So it is not reflexive. Sorry, symmetric. Okay. 1, 2 is there, but 2, 1 is not there. There itself, it fails actually. Then again, you can see 2, 3 is there, but 3, 2 is not there. That means again, it is not a symmetric. So one element, if the property fails at somewhere, that means it is fails. It fails. Okay. So it is not a symmetric relation. I will take another example, another relation that is 1, 2, 2, 1. Just I am taking only this much. 1, 2, 2, 1. Is it symmetric? Yes. 1, 2 is there. Again, 2, 1 is there. 1 is related to 2 and also 2 is related to 1. So it is a symmetric relation. But is it reflexive? No. Okay, because 1 is not there, so it is not reflexive. Okay, your 2 is not there, so it is not reflexive. Now the third one, that is the transitive relation. Okay. When we say that a relation in a set A is transitive. So what is the definition of transitive? Okay. R is a relation, so R is said to be transitive. A relation R in a set A is said to be transitive. What is the definition? Everybody knows. Okay, just I'm recalling. Suppose AB belongs to the relation. Okay, A is related to B, and also BC is in the relation. BC is in the relation. Okay, AB is in the relation, and also BC is in the relation. Then AC must be there in the relation. Yeah, implies AC belongs to the relation. Okay, that means if A is related to B and B is related to C, then A must be related to C. Okay, if AB is there, BC is also there, then AC must be there. Then only it will be transitive. And the definition we have to be very careful. Okay, if AB there, AB is there, BC is there, then only we have to think about AC. Suppose only AB is there. Okay, only AB is there. There is no BC. Then also it is transitive only. Then also it is transitive only. Okay, it is not breaking our definition actually. The definition says that along with the AB, suppose BC is also there. Along with the AB, suppose BC is also there, then AC must be there. Okay. Sometimes this definition is so much confusing also for some students. That's why I'm telling. Okay. So for example, I will take an example. Same set 1, 2, 3. Okay. R is equal to 1, 2, 2, 3, 1, 3. 1, 2, 2, 3, 1, 3. So let us check. Is it reflexive? No, it is not reflexive. 1, 1 is not there. No. 2, 2 is not there. 3, 3 is not there. So not reflexive. What about symmetric? 1, 2 is there, but 2, 1 is not there. There itself we can say it is not a symmetric. Okay, 1, 2 is there, but there is no 2, 1. What about transitive? 1, 2 is there, 2, 3 is there. Then you can see 1, 3 is there. You know? 1, 2 is there, 2, 3 is there. So also 1, 3 is there. That means it is transitive. Okay, we have to check all the possibilities actually. Okay, we have to check all the possibilities. Different pair we have to take actually. So again, you see, if I take 1, 3 is there, but there is no other element starting from 3 actually. Okay, so there is no problem. Otherwise, if I take first 2, 3, again, there is no element starting from 3. Okay, but we have to check all the possibilities. Okay, let me take another example. R2 equal to 1, 2, 2, 1, 1, 1. The same set, okay? Set is 1, 2, 3. Set A is 1, 2, 3. And my relation is 1, 2, 2, 1, 1, 1. Now you tell me the answer. You can put in the chat box also, okay? Is it transitive? That's the question. Is it a transitive relation? That's my question. So please type the answer in your chat box. Okay, some responses are here. Okay. Yes, some people are saying yes, and some people are saying no also. Okay. So which one will be taken? Okay. So the answer is no. It is not a transitive relation. Why? Why? Okay, 1, 2 is there, 2, 1 is there. Then some people are thinking only the okay, 1 is 1, 1 is there. 1, 1 is there, no. So what's the problem? We have to take in the other way also. We have to check all the possibilities. Okay. Suppose I take 2, 1 first. 2, 1 is there and 1, 2 is there. Then according to our definition, AB is there, BC is there. So according to our definition of transitive relation, 2, 2 also must be there. Okay. 2, 2 also must be there. But there is no 2, 2 here. Okay. So it is not a transitive relation. Sometimes you may commit mistake here. No? We will check only the one possibility. We are not checking the other possibility. Okay, we have to check all the pairs, different possibilities actually. Yeah? All the possible pairs we have to take and check. So 2, 1 is there, 1, 2 is there, but 2, 2 is not there. 2, 2 is not there. That means it is not a transitive relation. Clear? Okay. Now let me take another example on the same set, okay, R3. I am writing only 1, 2. I am writing only the element is the relation is 1, 2. 1, comma 2. Again, the question is whether it is transitive or not. Whether it is transitive or not. So I want the answer from you. So please give your response in the chat box. Let me see. Okay, different opinions are coming here also. Yes, no, different answers are coming. Okay, so I think some people knows the answer, know the concept very clearly, and some of you is not clear. That's why. Okay. So what is the definition of the transitive relation? I already told you. If AB is there, along with AB, BC is also there, then only we have to think about AC. Okay. If AB is there, along with AB, BC is also there, then only we have to think about AC. That is the definition says. Okay. It doesn't say that BC must be there always. Is it says like that, the definition? The definition does not say that along with AB, along BC must be there. No, it is not saying like that. If AB is there, and BC is there, then only AC must be there. Okay, then for transitivity. Okay, so it doesn't say that BC also must be there. So that means 1, 2 alone, the element 1, 2 alone is transitive. Okay, by default, we can say it is transitive. We cannot disprove that it is not transitive. Okay, so remember, it is transitive. Don't think that for transitivity, there must be two elements, means two ordered pairs must be there. No, not like that. If it is like that, then only we have to think about the AC. Now I write another relation. Okay, 1, 2, 1, 3. Same set. My set is same. Set A is 1, 2, 3. And the relation is R4 equal to 1, 2, 1, 3. Okay, again, give me the answer. Whether it is transitive, that's my question. Whether it is transitive. This relation is transitive or not. Okay. Different responses are coming. I think now most of the students are giving the correct answer. Okay. It is transitive. Transitive. Very good. Okay. 1, 2 is there. 1, 3 is there. Okay. So 1, 2. There is no element other any ordered pair starting from 2. Okay. So it is over there itself. 1, 3. And there is no element starting from 3. So to check transitivity. Okay. So again, it is just over there only. 1, 3. Sorry. In the anyway, you take. Okay. So it is transitive. Okay. It is very clearly transitive. Very good. So that's the meaning of transitive relation. So if a relation satisfies all the three properties, then we say that it is an equivalence relation. So generally, a question will be asking in the examination to check a relation is symmetric or reflexive, symmetric, transitive. Yeah, prove that it is an equivalence relation like that. Okay, now we will discuss some problems based on this equivalence relation. Okay. I'm taking a very simple example. First, so A is equal to a set 1, 2, 3, 4, 5, 6, 7. And we define a relation R is equal to set of all ordered pairs AB such that A minus B is divisible by 3. A minus B is divisible by 3. Both A and B are belongs to the set A. Okay, very simple example. Many of you may be knowing also. Just I want to tell about the equivalence classes. Okay, that's why I have taken this example. Okay, so very easily we can show that this is an equivalence relation. Okay, for example, the first property, reflexive. Reflexive means we have to prove that every element is related to itself. Okay. So we have to prove that A comma A always belongs to the relation for every A. So that is very clear. How to prove that A belongs to the relation? The relation is A minus B must be divisible by 3. A minus B must be divisible by 3. So, but we know that A minus A minus A means 0, which is always divisible by any number. So, which is divisible by 3. A minus A means 0. So, 0 is divisible by 3. Okay, this is true for every A in the set. Okay, for reflexive relation, remember this property must be true for every element. Okay, actually, we cannot write write each element 1 minus 1, 2 minus 2, 3 minus 3, up to 7 minus 7. No need to write like that. In general, we write like this. So it is clear that for all A belongs to the set. Some students may be writing 1 minus 1 equals 0, 2 minus 2 equals 0. No need to write like that. Okay, in general, you have to write like this. That's all. For any element, A minus A is always 0. So it is reflexive. Okay, it is reflexive. R is reflexive. Then come to the second, that is the symmetric. How to write the answer symmetric? For that, let A comma B belongs to the relation. Symmetric relation. What we have to prove that if AB is there, then we have to prove that BA also there. BA is also there. So we start with the AB belongs to R. Suppose AB is in the relation. Okay. So if AB is in the relation, what is the definition says that, which implies A minus B is divisible by 3. This is our given relation. A minus B is divisible by 3. And we know that whenever A minus B is divisible by 3, B minus A is also divisible by 3. You know? That's a very simple fact actually. So which implies B minus A is the negative of A minus B actually. So that is also divisible by 3. So whenever A minus B is divisible by 3, it is always true that B minus A is also divisible by 3. So that means the relation, which implies B comma A belongs to the relation. B is related to A. So it is symmetric. It is symmetric. Now, the third one, transitive. Transitivity. So again, remember the definition. What is transitive relation? If AB is there and along with AB, BC is also there, AC must be there. So we start like this, okay? We assume that let AB belongs to the relation and Hmm.
Can I come there once?
Okay.
Yeah, good.
Going right?
Yes, sir. Good.
Okay, children. Due to some connectivity issues, there was some interruption actually. So it is okay. I don't know whether this discussion uh, you have seen or not. What I have taken is the set 1, 2, 3, 4, 5, 6, 7, and we have proved that this is an equivalence relation. Okay, we have proved that this is equivalence relation, and what are the equivalence classes that I am discussing actually? What are the equivalence classes? So you take a particular element 1 from the set 1, then we list out all the other elements of this set which are related to 1. Okay, which are related to 1. So very clearly, the elements are 4 and 7. So 1, 4, 7, they forms a group, means they form a set. So all the three elements of this set are related to each other. Clear? Now you take another element to say 2. Then the other elements of this set which are related to 2 is 5 only. So 2, 5. That is a different set that form a different group actually. Okay. Now take another element that is 3. Then the other element, other elements which are related to 3 is 6 only. So 3, 6. 3 and 6 form a different set. So these three sets are known as equivalence classes. Okay, equivalence classes. So we denote every equivalence class by taking one of the element and writing in this way in a bracket. Okay, you can take any element from that set. Generally, we prefer the first element. Equivalence class 1. And second equivalence class, we write it as 2. And third equivalence class, we write it as 3. So our relation A minus B is divisible by 3. Divide this set, partitions this set into 3 mutually disjoint sets, and each set is called an equivalence class. Sometimes question may be asking, after proving the relation as an equivalence relation, write the equivalence classes. So in this way, we have to write the equivalence classes. Okay, so that's about relations and functions. So now I am going to discuss some problems from this area. Let us take the question is S be the set of all real numbers. The set is set of all real numbers, and R be a relation in S defined by R equal to all ordered pairs AB such that 1 plus AB greater than 0. That is the relation. Okay. 1 plus AB greater than 0. Show that R is reflexive, symmetric, but not transitive. What you have to done is also very clearly given in the question. Show that it is reflexive, show that it is symmetric, and it is not transitive. Okay. So the relation is like this. The relation says that A is related to B if 1 plus AB must be greater than 0. That is our relation. 1 plus AB must be greater than 0. Then we say that A is related to B. Yeah, A comma B is in the relation. Clear? So first thing is we have to prove it reflexive. We have to prove reflexive. So first one, reflexive. For reflexive, what we have to prove? A comma A belongs to the relation. Okay. For that, what we need to prove? A means what we have to prove? 1 plus A into A greater than 0. If that is true, then that means A belongs to the relation. That's very clear. 1 plus A into A. 1 plus A into A means 1 plus S square. 1 plus S square is always greater than 0, we know. Okay. That only we have to write. Okay. We know that 1 plus A into A. Yeah, A into A means S square is always greater than 0. For reflexivity, we need to prove 1 plus A into A is greater than 0. That is 1 plus S square greater than 0. It's always true. Okay, which is always true, comma. That means the relation is reflexive. Very clearly, this relation is reflexive. Okay. Now transitivity, sorry, symmetry, symmetric. Symmetric. For symmetric, what to do? We assume AB is in the relation. Then we will prove that BA is also in the relation. Okay. So let AB, A comma B belongs to the relation. So which indicates, which implies 1 plus AB is greater than 0. That is the relation. 1 plus AB greater than 0. So which implies 1 plus BA is also greater than 0. Isn't it? AB is same as BA because A and B are real numbers actually. Okay. The relation is on the set of all real numbers. So A and B are real numbers. So AB is same as BA in real numbers. That is very clear. So 1 plus BA is greater than 0. So 1 plus BA is greater than 0 stands for what? BA is in the relation. Okay, this is the condition required for BA. BA is in the relation. That means it is symmetric. Therefore, the relation is symmetric. Now for transitivity. Transitive or not. In the question itself, it is given that we have to prove that it is not a transitive. So it is not transitive, it is not transitive is given. So you have to prove by an example. Okay, you have to give an example where why it is not a transitive. So how to give an example? It is not transitive means how to give an example? We have to give an example such that AB is there and also BC is there. BC is also there, but AC is not there. AC should not be there. Okay. In that way, we have to find an example. So that will give the answer. So think about that. Let us take, we have to find some numbers. Okay. A, B and C, such that 1 plus AB must be there. 1 plus AB is greater than 0. 1 plus BC is also greater than 0. But 1 plus AC is not greater than 0. So like that, we have to find some numbers actually. So let us take, we can find so lot many examples, okay? If I take A is equal to 4, B is equal to minus 1 by 2, C equal to minus 8, let's see. What about 1 plus AB? 1 plus AB means 1 plus 4 into minus 1 by 2. Sorry, 1 plus 4 into 1 by 2, okay? Let's see, 1 plus 4 into minus 1 by 2, that is very clearly greater than 0. And again, take another element, 1 plus BC. Such that that is also positive. Okay, let me check this example, okay? 1 minute. Okay, let me take a different example, okay? What I have taken first, that is not correct actually. We have to give an example which is not true actually, okay? So I take A is equal to 2, B is equal to 0, okay? So B is equal to 0, C is equal to 2. So in this way, if I take A equal to 2, B is equal to 0, so 1 plus AB means 1 plus 2 into 0, that is greater than 0. 1 plus 0 means 1 only. So 1 is greater than 0, that is correct. Then again 1 plus BC, 1 plus 0 into minus 2. That is also greater than 0. So what about 1 plus AC? 1 plus AC. A is 2 and C is minus 2. Okay. A is 2, B, C is minus 2. So 1 plus 2 into minus 2. That is 1 plus minus 4. So 1 plus minus 4 means that is very clearly less than 0. Okay. So the first three numbers what I have taken, that is not satisfying. Okay. So you can find so many examples in this way. So it indicates that 1, sorry, 2 comma 0. 2 comma 0 is in the relation. Okay, 1 plus 2 into 0 is greater than 0 means 2 0 is in the relation. And second condition, 1 plus 0 into minus 2. Okay, that means 0 minus 2 is also in the relation, but 2 comma minus 2. Okay, AC 2 comma minus 2 is not in the relation. Okay, so AB is in the relation, BC is also in the relation, but AC is not in the relation. You can find other examples also. You find some values of A, B, C. Okay, the first condition must be satisfying, but the third condition is not satisfying. So very clearly, by giving a numerical example, we can prove that this relation is not transitive. Okay. Now, let's take let us be the set of all real numbers and show that the relation R equal to or all ordered pairs AB such that A square plus B square equal to 1 is symmetric, but neither reflexive nor transitive. The relation is A square plus B square equal to 1. Set is the set of all real numbers. Okay. So it is very simple, I think. It is not reflexive. Why it is not reflexive? For reflexivity, what is the condition? A must be related to A. For every real number, A must be related to A means what's the meaning actually? For every real number, A square plus A square must be 1. If it is true, for every real number, if it is true, then we say that it is reflexive. Is it true? Always A square plus A square equal 1? No. Very clearly, this is not true for every real numbers A. Okay. So that we have to write. Okay. It is not true. It is not true that S square plus S square equal to 1 for all real numbers A. For all real numbers A. S square plus S square equal 1 means actually 2S square equal 1. No, 2S square equal 1 means S square is 1 by 2. S square is 1 by 2 means A is equal to plus or minus 1 by root 2. So only that in that particular case only it will be satisfying. So there are so many numbers without satisfying this property. So very clearly this is not true for every time. So it is not a reflexive. Clear? Therefore, the relation is not reflexive. Not reflexive. What about symmetry? The second symmetric. Is it symmetric or not? Okay. So for that, what to do? Let AB is in the relation, which implies S square plus B square is equal to 1. S square plus B square equal 1. So whenever S square plus B square equal 1, we know that the reverse way also, B square plus S square is also equal to 1. Isn't it? So that means BA is also in the relation. So whenever S square plus B square equal 1, B square plus A square is also 1. No change, no? That means the relation is symmetric. Now transitive. Third one. Transitive or not? You think about that. Suppose S square plus B square equal 1. And B square plus A square is also equal 1. S square plus B square equal 1. B square plus A square is also equal to 1. Then is it true that S square plus C square equal 1? Always, if it is true, if S square plus B square equal 1 and B square plus A square equal 1, then if it is true, S square plus A square equal 1, then only it will be transitive. So what is your opinion? Okay, let me check your chat box. Is it transitive? Some comment is there. Your screen is not visible. I think it is the earlier comment maybe. Yeah? Okay, now it is visible, I think. There was some problem with the in between. That's why. So no response is there. I could not see any response here. Is it transitive or not? That's my question. If it is not transitive, we have to give an example. A numerical example you have to give. Okay, let us take we know 1 square plus 0 square equal to 1. Okay, 1 square plus 0 square equal to 1 means S square plus B square equal to 1. So what we can say that then 1 comma 0 is in the relation. 1 comma 0 is in the relation. Also, in the other way also we can say 0 square plus 1 square equal to 1. Okay. That means what we can say 0 comma 1 also in the relation. 0, 1 is in the relation very clearly. So AB is there, BC is there. So what about AC? What about AC? Is it true that AC means 1 square plus 1 square, no? A is 1, C is 1. So S square plus A square means 1 square plus 1 square. 1 square plus 1 square equal 1. Is it true? It is not true very clearly. So we have tried, but 1 square plus 1 square equal 1 is not true. Yeah, not equal 1. Okay, that indicates that 1 comma 1 is not in the relation. 1 comma 1 is not in the relation. It is enough to disprove one property. If you want to disprove it, one numerical example is enough. 1, 0 is in the relation very clearly. 1 square plus 0 square is 1. 0, 1 is also in the relation because 0 square plus 1 square equal 1. That is both are true. But 1 square plus 1 square equal 1 is not true. Very clear that is not true. That means 1, 1 is not in the relation. So it is not a transitive. It is not a transitive. Only these are all not only the examples. Okay, you can find by yourself also. You try to find a different values of ABC. Okay, that is up to you. Find out different values for ABC. Okay, to disprove it. Now take another question. This is also a very important question actually. Very, very important question for examination. Many a times this question, yeah, this type of question has asked in the examination. Okay. So the relation is A is at 1, 2, 3 up to 9. 1, 2, 3 up to 9. And R be a relation in A cross A. Remember, the relation is in A cross A. Okay. The set is A cross A. The set itself is A cross A. Defined by AB related to CD. AB related to CD if and only if A plus D equal to B plus C. A plus D equal to B plus C. Where AB and CD belongs to A cross A. So prove that R is an equivalence relation. R is an equivalence relation. Also obtain the equivalence class determined by 2, 5. So this is the question. So the relation is like this. One element is AB. Okay, remember every element of A cross A. The set itself is A cross A. So that means every element in our set is of the form A comma B. All elements are ordered pairs. Remember. So any element AB is related to another element CD. Another element CD. If and only if the condition is what? A plus D equal to B plus C. A plus D equal to B plus C. That means the sum of the first and last must be equal to sum of the second and third. In that way, we have to identify, means understand the relation. Okay, how it is given. Okay, A plus D, first plus last, equal to second plus third. That is the relation. If it is if this condition is satisfied, that means AB is related to CD. AB is related to CD. Okay. So first thing we have to prove it is reflexive. Okay. Reflexive. Reflexive. So what we have to prove for reflexivity? Every element is related to itself. Okay. In our definition, what we have studied, A is related to A. If the element is A, okay, if the element is A is related to A. But here the element itself is an ordered pair. Okay, element itself is an ordered pair. So every element is ordered pair AB. So what we have to prove that AB is related to AB. AB is related to AB. I am why I am telling that some students commit mistake here also. They will take AA related to AA in that way. Not like that. Okay, every element is AB. So that particular element must be related to AB itself. That is the meaning of the reflexivity. So we have to prove that AB related to AB. This is what we have to prove. AB related to AB. That means what we are required to prove? The relation is like this, no? A plus D means first plus last. A plus D means here A plus B. That must be equal to the second plus third, B plus A. Okay. So we'll write like this. Okay. To prove that AB is related to AB. AB is related to AB. So that is to prove A plus B. Okay, A plus B is coming, the first plus last. A plus B equal to B plus A, second plus third, B plus A. Okay, that is to prove that A plus B equal to B plus A. And you know that A plus B is always B plus A because A and B are real natural numbers, something. No? What is given the set, if it is any real number, or no problem. Anyway, the given set is 1, 2, 3 up to 9. Okay, natural numbers. So very clearly, A plus B must be equal to B plus A. That is always true. Okay, comma, which is always true. We know this property, commutative property. Huh? A plus B is always B plus A for any real number also. So that means we have proved that every element AB is related to the same element itself. AB related to AB for all element. Okay, this is true for every element A comma B. For all AB belongs to the given set across A. So it is reflexive. Okay, it is reflexive. The conclusion is reflexive. Or is reflexive. Now symmetric. What about symmetric? So how to prove symmetric? For symmetric, what we have to prove? Suppose one element is related to another element. Okay, then we have to prove the other way. The second element is related to the first element. So we have to start like this. Okay, let the one element, yeah, first element AB is related to another element, that is CD. All the elements are ordered pairs A, B, C, D, X, Y, E, F, like that we can take. So suppose AB is related to CD. So that means what? By definition, this says that A plus D, okay, A plus D is equal to B plus C. A plus D is equal to B plus C, isn't it? So the relation is like this: A plus D equal to B plus C. First plus last equal to second plus third. Now we have to prove in the other way. CD is related to AB. CD is related to AB. Okay. CD comes first. CD related to AB means what we need to prove actually. What we need to prove? C plus B equal to D plus A. That is our target. So we have to prove C plus B equal to D plus A. For that, we will do some modification here. We will reverse this equation. So B plus C equal to A plus B, A plus D. A plus D and B plus C interchange each other. B plus C equal to A plus D. And B plus C, you can write it as C plus B. B plus C is same as C plus B. And A plus D is same as D plus A. No, A, B, C, D are all natural numbers only. So commutative property is true there. A plus B same as B plus A. Okay. So we got C plus B equal to D plus A. So that is the required. C plus B equal to D plus A. That is the required statement. Which implies what? Now CD. Okay. CD is related to AB. CD is related to AB. Okay. So therefore, this relation is transitive. Sorry, symmetric. Now the third one. The third one, transitive. I think in the second heading I have written transitive. No? That is wrong. We have proved it. Sorry, symmetric. Correct? No? Okay. Now it is. We have to prove it is transitive or not. For transitivity, the same method. What we do? We take some element AB and suppose that that is related to a second element CD. Okay. First element is related to CD, second element CD, and the CD, the CD element, second element is related to another element. Another element you can take EF, XY, anything. All the elements must be ordered pairs only. That's all. Okay. So we assumed that AB is related to CD and CD is related to EF. Now what we have to prove? AB is related to EF. That is our target. Okay. AB is related to EF. So AB related to CD. What it indicates by definition, this says that A plus D must be equal to A plus D must be equal to B plus C, B plus C, and the second statement says that C plus F is equal to D plus E. Okay, C plus F is equal to D plus E by definition of the given relation, isn't it? Okay, now from here, actually what we need to prove, AB is related to EF, isn't it? So that means we have to prove A plus F must be equal to B plus E. A plus F must be equal to B plus E. That is our target. Okay. So how to get that one? We have two equations with us. We have two equations with us. So we have to use these two equations. We have to use these two equations and prove A plus F equal to B plus E. For that, some algebra actually. Okay. Let us do like this. Let us add it. Add these two equations. Okay. Adding means left side and left side we will add together. So A plus D plus E plus F. A plus D plus E plus F equal to B plus C plus D plus E. Okay, bracket is not required anyway. So A plus D plus E plus F equal to B plus C plus D plus C. We have added these two conditions. Now you see both sides, some common terms may be there. So that can be cancelled. What is common here? C and C will cancel. Okay. Then D also common. D. So what is remaining? What is remaining is A plus F equal to A plus F equal to B plus E. A plus F is equal to B plus E. Okay. So what it indicates? This is the required condition. No? This implies that AB is related to EF. AB is related to EF. Because A plus F equal to B plus E. That is the required condition. That is our definition of the relation. Okay. So that means it satisfies all the three properties: reflexive, symmetric, and transitive. This indicates that this is transitive. Okay. So our relation is an equivalence relation. Our relation is an equivalence relation. Clear? Now there is one more part actually for this. Once you know the relation is equivalence relation, equivalence classes will be formed. No? So the question also contains, also obtain the equivalence class determined by 2, 5. Okay, means the equivalence class containing the element 2, 5. That is the second part actually. So here the set, the set A is 1, 2, 3, 4, 5, 6, 7. Okay. And given element is 2, 5. So we have to find all the other elements of A cross A which are related to 2, 5. That is meant by the equivalence class. Okay. What are the other elements of that set A cross A? Set is A cross A. A cross A such that 2, 5 is related to that elements. Okay. So how to find it? Suppose we take that element as some xy. We don't know actually what are the other elements. Let xy is the element, yeah, generally the elements which are related to 2, 5. So by our condition, definition, what is the relation actually? Then 2 plus y must be equal to 5 plus x. If xy is related to 2, 5, so very clearly 2 plus y must be equal to 5 plus x. Okay. Otherwise, what we can say that in another way, y minus x must be equal to 3. So we have to list all those elements of A cross A satisfying this condition. Y minus x must be equal to 3. Clear? Once you got this relation, we can list out the elements now. One element is 2, 5 only. Okay. Therefore, the equivalence class containing 2, 5 means one element will be 2, 5 only. 2, 5 must be there. No? 2, 5 must be there. Then, if I take 3, 3, 6. No? 3, 6. 6 minus 3 is 3. So we have to list all the elements satisfying this condition y minus x equal to 3. Then you will get the equivalence class containing that element. Okay. 3, 6. The next element will be, you can say 4, 7. 4, 7. Because 7 minus 4 is 3. Okay. Any other element, if I can take a 5, 5, 8, but 8 is not there in the set, no? So we cannot take. So these are the only elements. So we can write this as the equivalence class containing 2, 5. We'll use this symbol for the equivalence class. So this is the equivalence class containing the element 2, 5. The element can be a different element also. Okay, in this question, the element is given 2, 5. In some other cases, some other element may be given. So accordingly, we have to write. Suppose the question is to find the what are the elements related to 2, 3, for example. Okay, you write the equivalence class containing 2, 3. So what is the method? The same idea. We take a general element. Suppose xy is related to 2, 3. So which implies 2 plus y must be equal to 3 plus x. Apply the relation. What is given the apply the relation. So 2 plus y equal to 3 plus x. That means we will get y minus x equal to 1. Y minus x equal to 1. So this is the condition we have to apply. So we have to list all the elements satisfying y minus x equal 1. Okay. So one element is 2, 3 already given. 2, 3. If the question is like this, write the equivalence class containing 2, 3. Then we have to do like this. Okay. 2, 3. Then 3, 4. Okay. 3, 4. Then 4, 5. No, 4, 5. Then 5, 6. Then 6, 7. So this will form another equivalence class. So we denote this as the equivalence class containing 2, 3. So I think it is clear how to write the equivalence class. Okay. Okay, some students have given some responses for the earlier uh, question. Okay, good. Now only I could see. Okay. So one doubt in transitive that A and C should be different, but you have taken same value. Why, sir? Who told you? It is not like that. Okay. You can take same value. In transitive, A and C should be different. Is it given somewhere like that? No. Some of you have commented that A and C should be different. Okay, A and C should be different. No, no need to, no need. Okay, we can take any counter example. For example, already I have given the example now. 1, 2. Okay, 2, 1. 1, 2 and 2, 1. So for transitivity, what we have to add? 1, 1. You know? And also 2, 2. So A is 1, B is 2. Okay. So B is 2 and C is 1. It can be like that. No? There is no condition that A and C should be different like that. Okay. Don't think like that. Okay. So we'll move on to another question. Function we will take later. Let us do some problems from this equivalence relation only. Okay. Another example, another question. Determine whether the relation are defined on the set of all real numbers given by A is related to B if A minus B plus root 3 belongs to S. A minus B plus root 3 belongs to S, where S is the set of all irrational numbers. S is the set of all irrational numbers. So relation is A is related to B. A is related to B if A minus B plus root 3 is an irrational number. That's the meaning. Okay. A minus B plus root 3 is an irrational number. That is the relation. A minus B plus root 3. If it is an irrational number, we say that A and B are related. That is the question actually. So we have to check reflexive, symmetric, and transitive. So what's your opinion? Is it a reflexive relation? That's my first question. I think this can be answered by everyone. Is it a reflexive relation? You can put in the chat box. Let me see. No comments, nothing I could see in the chat box. The question is clear, na? My question is whether this relation is reflexive or not. Reflexive or not. The relation is all. The definition is clear, na? A and B are related if A minus B plus root 3 is an irrational number. A minus B plus root 3 is an irrational number. Then we say that A and B are related. So my question is reflexive or not? Reflexive or not? So please give me a suggestion. Not reflexive. Okay. Not reflexive. JNV correctal. Not reflexive. JNV scale. Maybe Srikakulam. Yes. Reflexive. Reflexive, not symmetric. Okay. Good. Some responses are there. So what is meant by reflexive? Reflexive means we have to prove that A must be related to A. Okay, A must be related to A. When A must be related to A, if A minus A plus root 3 is an irrational number. Okay, A minus A plus root 3 must be an irrational number. Then we can conclude A is related to A. And it is true now, A minus A means 0, and 0 plus root 3 is always an irrational number. 0 plus root 3 means root 3 only. So root 3 is a rational number. So for any A, A minus A plus root 3 is always root 3, and that's equal to irrational number. So it is a reflexive relation. Very clear. Good. Now let's go to the symmetry. Symmetric, second part. All of you try, okay? You think about it. Symmetric. So please put your comment answer in the chat box. Is it symmetric or not? I want the response from your side. Not symmetric. Yes, symmetric. So different opinions are there. Yes, it is symmetric. Somebody is saying it is symmetric. Symmetric. It's an equivalence relation also. Somebody has concluded that it is an equivalence relation also. Okay. Anyway, you are trying. That's good. Okay. Okay, let us check. Okay. So some of you are saying that it is symmetric, and some of you are saying that it is not symmetric. Okay. So let us take some values for A. So take A is equal to 2 root 3. 2 root 3. And B is equal to root 3. Take A is equal to 2 root 3. B is equal to root 3. Then A minus B plus root 3. A minus B plus root 3 means what? 2 root 3 minus root 3 plus root 3. Okay. 2 root 3 minus root 3 plus root 3. And that's equal to 2 root 3. And very clearly, 2 root 3 is an irrational number. 2 root 3 belongs to S. 2 root 3 is an irrational number. So what it indicates that A is related to B. Okay. So which implies that 2 root 3 comma root 3 belongs to the relation. Belongs to the relation. Correct? Now you think in the other way. What about b minus a? Okay. So what about b minus a plus root 3? ba. b minus a plus root 3. So that is root 3 minus 2 root 3 plus root 3. Isn't it? b minus a plus root 3. So what is the answer? Very clearly it is 0. Is 0 is an irrational number? No. Very clear. 0 is a rational number. So that means this is not an irrational number. This is not an irrational number. So what is the meaning? AB is there, but BA is not there. Okay. AB is there, but BA is not there. Okay. So this, therefore, root 3 comma 2 root 3 is not in the relation. Not in the relation. Okay. Not here, yes, not yes. Okay. We have tried to the relation actually. 2 root 3 belongs to the relation, but root 3 2 root 3 does not belong to the relation. So that means it is not symmetric. Okay. Therefore, R is not symmetric. R is not symmetric. Okay. Now what about the transitivity? Transitivity. Third one. So check yourself. Okay. Can you give a counter example where it is not transitive? Try yourself. Is it transitive or not? If it is not transitive, why it is not a transitive? I think you may be trying. Okay. Okay. Let us take root of 3. A is equal to root of 3. And B is equal to some 1. And C is equal to 2 root of 3. You can take different example also. Okay. You might have got some other numerical values maybe. Anyway. Okay. So what is A minus B plus root of 3? A minus B plus root 3 means root 3 minus 1 plus root 3. Very clearly, it is irrational number. So belongs to S. Okay. So AB is there. Yeah, root 3 comma 1 is there. Root 3 comma 1 belongs to the relation. Belongs to the relation. Clear? Now, what about BC? Also, 1 minus 2 root 3 plus root 3. 1 minus 2 root 3 plus root 3. That is 1 minus root 3. That is also an irrational number. That is also irrational number. That means 1 comma root 3. Sorry, 2 root 3 is in the relation. Okay. 1 comma 2 root 3 is in the relation. Now what about AC? What about AC? A comma C means root 3 minus 2 root 3 plus root 3. The same idea of what we have used for symmetric to prove not symmetric. Same idea is applying here also. Okay. So A minus B, sorry, A minus C plus root 3. And very clearly, this is equal to 0. And 0 is not a rational number. 0 is not a rational number. That means this relation is not transitive. You know? Why? Root 3, comma 2 root 3 is not in the relation. Okay. Root 3 comma 1 is in the relation. Then 1 comma 2 root 3 is also in the relation. But root 3, 2 root 3 is not in the relation. So we can conclude that this is not transitive. This relation is not transitive. Okay. So it is reflexive, but not symmetric and not transitive also. Okay. You may find some other examples, means other values for ABC. Okay. Not only this one. To disprove one example is enough. One example, whatever the example, we can put. Whatever values we can put for ABC. Okay. You try to find some other values for A, B, C, C. Okay, some of you have given not a transitive, but not given the values. Okay, root 3, 2 root 3. Yeah, somebody have written root 3, 2 root 3. Yes, correct. Good. Now let us go to some other another question. Show that the relation are on the set n cross n. N cross n. N is set of all natural numbers defined by AB related to CD if AD into B plus C equal to BC into A plus D. The relation is AD into B plus C equal to BC into A plus D. For all A, B, C, D belongs to N. A, B, C, D are natural numbers. So show that it is an equivalence relation. Okay, show that it is an equivalence relation. This is also very important question. Many times asked in the board examination. Last year also, it was in the question paper. Annual CBSE board exam question paper. So almost same method, just like the one of the previous question. Okay. So the relation is like this. Okay. First, we have to understand the meaning, the definition of the relation. Everything is coming from here only. So AB and CD are related if that implies AD into B plus C. AD into B plus C equal to BC into A plus D. This is the condition. AD into B plus C. Okay. Product of A and D into sum of B and C. Product of AD, product of A and D equal to sum of B and C. Equal to in the other way. Product of B and C into sum of A and D. Okay. So this is the relation. So we have to verify whether it is reflexive, symmetric, or transitive. Okay. Let us see the reflexivity. Reflexive. So for reflexive, what we have to prove? For reflexive, we have to prove that AB is related to AB. AB is related to AB, isn't it? AB is related to AB. For that, what we need to prove? What we need to prove? Product of first and last. Okay, that is to prove. That is to prove that product of first and last, that is A into B, AB into B plus C. Okay, B plus means some of the other two elements. B plus A here. Product of first and last means A and B, AB, and the sum of the other two, B plus A. Is equal to, in the reverse way, okay, BA into A plus B. According to this definition, okay, we are writing. So this is we have to prove. If this condition is true, that means it is reflexive. So we only need to check it is true or not. Very clearly we can see. We know A and B are natural numbers. Okay, A is a natural number, B is a natural number. So AB is same as BA. So there is no problem in writing AB as BA. And also we know that B plus A is same as A plus B. Commutative property, addition and multiplication is true in natural numbers. Okay, addition and multiplication is commutative in the set of all natural numbers. That's why AB you can write it as BA and B plus A is same as A plus B. Okay, so which implies AB into B plus A is equal to AB into B plus A. Otherwise, simply also we can say this is always true because addition and multiplication is commutative. Addition and multiplication is commutative in the set of all natural numbers. Okay, so it is always true, which is true. That means this relation is reflexive. Okay, reflexive over. Now let us go to the second, symmetric. For symmetric, so what to do? Let AB is related to CD. For symmetric, suppose AB is related to CD. So by definition, which implies what? Which implies what? AD into B plus C. AD into B plus C. AD into B plus C. Definition is equal to BC into A plus D. BC into A plus D. Isn't it? Definition. Actually, what we have to prove actually, that also we have to see, okay. We need to prove that CD is related to AB. CD is related to AB. For that, what is to prove? CB into D plus A equal to, okay, CB into D plus A equal to DA into C plus B. That is the required condition. So from here, we have to reach that condition, okay. CB into D plus A. So let us reverse this equation, okay, reverse. So BC into A plus D, write in the left side, and right side you write AD into B plus C. We always see the required answer. What is the required answer? Accordingly, we will make the modification here, okay. We need to prove that CB into D plus A. So now this BC can be written as CB because BC and CB are same only, and A plus D is same as D plus A. Okay, the reason is addition and multiplication both are commutative in the natural numbers, set of all natural numbers. Okay, and that's equal to this AD can be written as DA. AD is same as DA, and B plus C is same as C plus B. In bracket, you can mention addition and multiplication are commutative in the set of all natural numbers. That's why we are able to write CB as BC and D plus A as A plus D. Okay. Now I think that this is the required condition. No? So this indicates CD is related to AB, isn't it? CD is related to AB. So it is symmetric. So we have proved that this is symmetric. Clear? Now the third one means the last property, that is transitive. Okay. For transitive, transitive. What is the mean? What is the definition of transitivity? Suppose AB is related to CD, and also CD is related to some EF. CD is related to EF. So we have to prove that AB is related to EF. Okay. So which implies AD into B plus C equal to, for the first condition, you will get AD into B plus C equal to BC into A plus D. BC into A plus D. Then from the second, what you will get? CF into D plus E is equal to DE into C plus F. We are applying the given definition of the relation, okay, everywhere. AD into B plus C equal to BC into A plus D, first condition. Then CF into D plus C equal to DE into C plus F, second condition. Now, using these two conditions, we have to prove that AB related to EF. Yeah, that is what we have to prove actually. AF into B plus E equal to, okay, AF into B plus C equal to BE into A plus F. For that, we have to do some algebra, okay. So different way we can do. One method is just B plus C by BC. You take BC here, so B plus C by BC equal to A plus D by AD. Rewrite. And second equation also. Okay, you can write D plus E divided by DE equal to C plus F divided by CF. Isn't it? So which implies we can separate it. B by B plus C means 1 by C plus 1 by B equal to 1 by D plus 1 by A. And second equation, 1 by E plus 1 by D equal to 1 by F plus 1 by C. Dividing by BC, AD, D, etc. Therefore, now we have two equations and both we will add together. Okay, therefore adding, that is 1 by C plus 1 by B plus 1 by E plus 1 by D equal to this 1 by C plus 1 by B plus 1 by E plus 1 by D. Right side also 1 by D plus 1 by A plus 1 by F plus 1 by C. That will give the answer. Okay. So from both sides, we can cancel the common terms. 1 by D is common. Okay. Then what is another? 1 by C. Okay. 1 by C is common. Cancel it. Remaining is 1 by B plus 1 by E. That can be again cross multiply. So this will be equal to B plus E divided by BE. And right side 1 by A plus 1 by F means that is A plus F divided by AF. Okay. Then if you cross multiply, that will give the answer. AF into B plus C equal to BE into A plus F. AF into B plus C equal to BE into A plus F. And that is the required condition, isn't it? We have to prove that AB related to EF. That means AF into B plus C must be equal to BE into A plus, sorry. AF into B plus C is equal to BE into A plus F. Correct. That is the at last we will get that one. AF into B plus C equal to B into A plus F. That means it is a transitive relation. So it satisfies all the three conditions, all the three properties. So it is an equivalence relation. Okay. So I think the time is already 8:30. So we have to stop here and we will meet again in the afternoon. Okay. 2:30 p.m.